Alright, so the last section of topic 5 is over something called geometric sequences and series. You guys actually started learning about sequences last semester. You did arithmetic sequences. And this one's just a little bit different because now we're going to involve some exponents, which is what you learned about at the beginning of this topic. This is the last section. I think you'll find it a little bit easier than the logarithm stuff that we did in 5.6 and 5.7. Those were definitely the two hardest sections. This will be a little bit more straightforward. I think you'll enjoy it. So, first of all, what the heck is a geometric sequence? I'll start with your guys' definition. Let me switch to black here. Alright. So a geometric sequence is a sequence with a constant ratio between consecutive terms. So a sequence meaning like 2, 4, 6, 8, for example. That was one of the arithmetic sequences you guys learned last semester because you add 2 every time. Now you have a constant ratio between it, and that constant ratio is called your common ratio. And you'll see it with, You'll see it written as the letter R, which is what I was trying to write there. So your common ratio is letter R. When you have a ratio, that means that you're multiplying something. So for example, you could have 1, 3, 9, 27. Now your sequence is multiplying by 3 every time. That's a geometric sequence. Then the first thing we're going to talk about is writing a recursive definition. So this is kind of a math formula. It'll look complicated, but I'll explain it after I write it. Okay, so this is an example of a piecewise function, which you haven't really learned that much about. Basically, just think of it as it's a function in 2 chunks. You have the top row and the bottom row. The top row is really straightforward. This just means A1 means your first term. And N is the term number. So the first row makes a lot of sense because when n equals 1, this n stuff on the right side, that's called like a condition. So this is saying when n equals 1, this is what happens. And then in the second row, when n is greater than 1, this is what happens. So in the first row, you have when n equals 1. So when you have your first term number, that is your first term. That's what that first row is saying. It's very straightforward. Then the next row, this one's a little bit more complex. You have a n minus 1. So that means the previous term, okay? Because if you're looking at the fourth term, the one previous to that would be the third term. That's 4 minus 1. R is your common ratio. And then n is still your term number. So now you're talking about, whenever you're talking about the second term, third term, fourth term, fifth term, anything that's bigger than 1, you multiply the previous term times the ratio, okay? So a n minus 1 times r, that means multiplying the previous term times the common ratio. So if you think about the geometric sequence 1, 3, 9, to get my second term, I multiply, because you'll notice I'm multiplying times 3 every time. I multiply the previous term, 1, times 3 to get 3. That's what that second row is saying. So let's do an example. It might make more sense. On example 1, it says, is the sequence shown in the table a geometric sequence? If so, write a recursive definition for the sequence. So you have in your left column your term number, so 1, 2, 3, 4, 5. And then you have the term, so 4, 12, 36, 108, 324. You always want to see if you're multiplying by the same thing every time when you're looking at your terms. So 4 times 3 gives you 12. 12 times 3 gives you 36. 36 times 3 gives you 108. And 108 times 324, or 108 times 3 gives you 324. Okay, so yes, this is a geometric sequence because each term is being multiplied by the common ratio of 3. So since I'm multiplying by 3 every time, that is what your R value is. So I could also say R equals 3. That's my common ratio. So since this is a geometric sequence, we're going to write the recursive definition for it. So using this up here to write it. So I always start with AN. That doesn't change. So split this up into 2 rows. So you always start with your first term, or A1. Okay. In this case, my first term is 4. Oh, I butchered that. I'll do a better job circling that. 4. So I'm going to put 4 right here, and then a comma. My term is 4 when I'm talking about the first term. So n is 1. That's always the same. Then I'm going to multiply my ratio times an minus 1. Up here, like right here, it says an minus 1 times r. When you actually plug in a number for r, though, you usually write it first. So I'm going to say 3, because r is 3, we just said that right here, times an minus 1. And that is when n is greater than 1. And that's all you have to do to write a recursive definition for a geometric sequence. So that would be my answer there. Now, on letter B, it says, instead of showing you a table, it just lists out the sequence. So you have 12, 9.6, 7.68, 6.144. Is it a geometric sequence? If so, write the recursive definition. So this one's obviously a little bit harder to see if you're multiplying by the same thing every time. So what you can do is take the second number and divide it by the first number to get your ratio. So I have 9.6 divided by 12. That gives you 0.8. You always want to check to make sure that it's the same ratio for every term. Is this being multiplied by the same thing every time? So I'm going to check. I'm going to do 7.68 divided by 9.6. So this third term divided by the second term. Plug that in a calculator. You also get 0.8. And then my fourth term divided by my third term, which, plug that in your calculator, you still get 0.8. So I know that R equals 0.8. Okay, so when you get a common ratio, when everything's being divided by the same thing, then it's a geometric sequence. So yes, this is a geometric sequence because R equals 0.8. Now I need to write my recursive definition. So again, the two pieces of information you got to know for this are R, which is 0.8, we know that, and then your first term, which you'll see it written as A1. My first term is just whatever's listed first, so 12. I'm going to plug that in to my recursive definition. So set up your piecewise bracket thing. So the first thing you plug in is your first term. So I know an equals 12 when n is equal to 1. And then I do my common ratio, so 0.8 times a to the n minus 1. And that is when n is greater than 1. And there's my recursive definition for that one. Alright, so that's recursive definition. Now we have explicit definition. So here's what an explicit definition looks like. I'll try to write it out kind of wide because I'm going to then write out what each thing means. So you have an equals a1 times r to the n minus 1. You'll often see it written like this, just to show you. That's the same thing. Parentheses still mean multiplication. So an is the nth term. So like if I say the fourth term, then that's what I'm trying to find, an. If I say the fifth term, that would be the fifth term, whatever. A1 is your first term. R is again your common ratio. It will always mean that when we're talking about geometric sequences. And then n is equal to your term number once again. So I know sometimes people get n and an confused. If I'm talking about the fourth term, n would be 4, an would be whatever the fourth term is in the sequence. So on example 2, it says, given the recursive definition, and it's written kind of weird, so I'm going to rewrite it down here so you can see it. It just put both of the rows in the same row. So this is what it would say if it was written correctly. So you have your recursive definition. What is the explicit definition? So there's two important pieces of information you got to pull from this to be able to write an explicit definition. I need to know my first term. So what the heck is A1? Well, again, that's whatever's written in the first row of your recursive definition. So in that case, this would be 5. Then I need to know my common ratio, which is in the second row. It's that coefficient in front of a to the n minus 1. Again, if you don't remember what things are, go back up to this recursive definition here, because it tells you what everything is. So I know that r equals 1/2. And that's all I got to plug in to my explicit definition. So using what we just wrote down in the above definition, I leave an alone. Whenever you're writing an explicit definition, just leave it. A1, we know, is 5. Then I put my common ratio in parentheses, so 1/2, and raise it to the n minus 1. That's your explicit definition. The reason we leave an and n alone is because that's what you actually use to be able to find missing terms. So if I said, okay, go find the 20th term in this sequence, you could just plug in 20 for n and solve it that way. Do not, something that people do often, do not multiply 5 times 1/2 together. Remember PEMDAS. Okay, you do exponents before you do multiplication. So, since there's nothing in the exponent, you can't actually simplify it. You would have to do that before you can multiply 5 and 1/2 together. So do not do that. Just leave it be. I know it feels kind of awkward, but that's how it is. That's the rules of your order of operations. So go ahead and flip to the next page. So then it says, given the explicit definition, so now we're going to do the reverse. Given the explicit definition, an equals 3 times 2 to the n minus 1, what is the recursive definition? So you got to pull what you know from that. Again, the first number, go back to this definition right here. The first number is your A1. So A1, in this case, would be 3. And then the number in the parentheses is your common ratio. So that would be 2. Now I'm just going to plug that in to the definition of a recursive definition. So I have an, oops. There we go. The pen just stopped working for a second. An equals, set up my piecewise bracket. I have my first term, which is 3. My first term is 3 when n equals 1. And then I do my common ratio times n minus 1 when n is greater than 1. And there's my recursive definition. That's all you got to do on that one. Done. Then example 3. So here's a bit of an example of a more word problem type thing. It says, a phone tree is when one person calls a certain number of people, then those people each call the same number of people, and so on. So, this was a real thing before we had like emergency texts and stuff, where one person had to call people, and that way you could actually call everyone in your organization to let them know something was going on. So the first person calls 3 people, and they each call 3 people. In the 5th round, 243 people are called. So, you have this one person at the top. They call 3 people. Each one of them, they call 3 people. And so on. So it gets very big very quickly, okay? We consider this the first round because that's the first place where there's action. Then there's the second round, and then so on. So that's kind of that idea. It's kind of similar to COVID right now, because if you spread it to 3 people or whatever, then those people can spread to 3 people, and that's how it's gotten to be such a problem. So it's growing exponentially. So to figure out an explicit definition, you need to know 2 pieces of information. You gotta know the first term, and then you gotta know your common ratio. So my first term I have is 3, because that's that first round right here. Then my common ratio, if you think about what this is, 3, in my second row here I have 9 boxes, so 3, 9, and so on. We don't know what the third and the fourth term is just from the problem, but we do know that the 5th term is 243. That was given us here in the problem. So I'm multiplying times 3. Okay, 9 times 3 gives me 27. 27 times 3 gives me 81. And 81 times 3 does give me 243. Okay, So my common ratio that I'm multiplying by here is 3. That comes from them calling 3 people. So I just got to plug both of those in to my formula. And I have an equals 3 times 3 to the n minus 1. Your first term times your common ratio to the n minus 1. So that's my explicit definition. Then, figuring out how many people are in the 8th round, that means that's your 8th term. Okay, so I know that n now equals 8. All I need to do is plug that into that explicit definition that we just came up with. So I have an equals 3 times 3 to the 8 minus 1. When you do this, be sure you follow the rules of PEMDAS, or else you can easily screw up your answer. Okay, so figure out what's in your exponent first. So that becomes a 7. Then make sure that you do your exponent before you multiply. Do not do 3 times 3 and then raise it to the 7th power. Okay, do 3 to the 7th first. So I have 3 times 3 to the 7th. So you would plug 3 to the 7th into your calculator, which should give you 2,187. Then you just got to multiply those together. Let me do that real quick. And it should give you 6,561. So that means in that 8th round, 6,561 people were called. So you can see how this could be very effective when you're talking about call tree. Not so effective when you're talking about spreading a disease. So there you have it. If you have questions, schedule a Google Hangout with me. Send me an email, DM me on Instagram, whatever.